Now we're going to start talking about related rates. All right, so if we have a variable y and y changes with time, then the rate at which it changes is dy dt. All right, so let's look at an example of a variable that changes with time. So let's say that y is the height of a growing boy. Okay, so that changes with time, and let's say this is our function y. Y is equal to 70 minus 30. Let's assume that t is years and y is inches. So y is the boy's height at a given year. And let's assume that this equation holds from 10 years to 13 years, from when the boy is 10 years old to when the boy is 13 years old. Okay, so this is sort of a growth function. And if we want to know at what rate is this boy growing, we would just differentiate this equation with respect to t. So dy dt is equal to 7. All right, that's the derivative of the right-hand side. Now what does this 7 represent? It represents the rate at which the boy is growing. So the boy is growing about 7 inches a year, 7 inches per year, because those are our units, inches and years. All right, so this is the rate is 7 inches per year. That's dy dt. All right, now this topic is called related rates. All right, what we're really talking about here, what we're going to be talking about, we're going to be talking about two variables like x and y, which are related to one another, and x and y change with respect to time. And we want to know how are the rates at which they are changing related. All right, so let's look at an example like that. So here we have two variables that are related, y and x, and they're related by this equation, y is equal to 2x. So, okay, so y and x are related. And let's assume that both x and y are changing with respect to time. So to make it concrete, let's suppose x is a distance that person A is walking, and y is the distance that person B is walking. So we have two people walking. Now notice that y is equal to 2x. So that means that the second person B is covering twice as much ground as the first person A. All right. So the distance that he's covering is twice the distance that the first person A is covering. Now, what about how quickly this person is walking compared to how quickly this person is walking? All right, well, to get the rates at which we're walking, what we're going to do is we'll just differentiate both sides with respect to WRT, with respect to t, where t is time, even though t does not appear in this relationship, we can still differentiate both sides with respect to t. And the way we would do that is simply write the left side, the derivative of y with respect to t is dy dt. And then we have 2 derivative of x with respect to t is dx dt. So this is an equation of related rates now. dy dt is a rate, dx dt is a rate, and this says the rate at which person B is walking is twice the rate at which person A is walking. That's what this says. dy dt is equal to twice dx dt. And that's what we suspected. If this person B is covering twice as much ground as A, then he's walking twice as fast. So that's what this equation says. All right, so this equation is our related rate equation, or related rates equation. Now here we have another equation that represents a relationship between x and y, and we're told that x and y are changing with respect to t. So it makes sense to differentiate then with respect to t. All right. In fact, you can think of this, if you want, as, I'll just write it in parentheses, y of t is equal to x of t squared. All right, so differentiating both sides, that's what we want to do now. We want to differentiate with respect to t, even though t does not appear in this relationship. So on the left-hand side, we write dy dt. On the right-hand side, we have to use a chain rule, bring down the 2, reduce that exponent by 1, and multiply by the derivative of the inside. So here we're multiplying by x prime of t, but we're going to write that as dx dt. So this equation shows the relationship between dy dt and dx dt, and we can think of this as this is our related rates equation. Okay, here we have another one. Let's say we have y cubed equal x squared. And again, we just want to differentiate both sides with respect to t. So I'm assuming that y and x are changing with respect to time. Okay, so let's just practice doing that. So again, think of this as y of t cubed is equal to x of t squared. All right, so we're going to do a chain rule on the left and right. Bring the 3 down. Okay, y, and change that to 2. And now multiply by the derivative of the inside, which is y prime of t, but we're going to write that as dy dt. And here also bring the 2 down. X to the 1. Derivative of the inside is dx dt. All right, so that's how we differentiate both sides with respect to t. So now you're ready to do problem 8. So let me show you that problem. Okay, here's problem 8. We have y is equal to 3x to the 5th, and we want to find dy dt in terms of dx dt. In other words, differentiate both sides with respect to t. All right, so copy this one down. Okay, let's look at the next example here. All right, now let's suppose we have a third variable z. Suppose x, y, and z depend on t, depend on time, where z is equal to 5x and y is equal to 2x squared z squared. So we want to find dy dt in terms of dx dt. So it would be nice if we could do what we did before and just differentiate this and get dy dt on the left and something with dx dt on the right. The problem is we have this z over here. So we do what we typically do in these related rate problems. Usually what we have to do is first often we have to first get rid of an unwanted variable and then differentiate with respect to t. And here the unwanted variable is z, because we want dy dt in terms of dx dt. There's no mention of z here. So let's get rid of z. Well, that's why we have this relationship here. Z is equal to 5x, so we're going to substitute 5x instead of z, and in that way we'll get rid of z, and then we'll take the derivative with respect to t. All right, so what we're going to do is first substitute. So first we're going to I called it get rid of z, but I'll say first sub z equal to 5x. So into this equation, this is the equation that we're going to that we want to differentiate with respect to t. So we have y is equal to 2x squared, and instead of z squared, we have 5x squared. So that's the substituting right there. Okay, instead of z squared, we substituted z equal to 5x, and we have here, just simplify this, 5 squared is 25. 25 times 2 is 50. Okay, so and here we have x squared times x squared, which is x to the fourth. So this simplifies to 50x to the fourth. All right, so we have y is equal to 50x to the fourth. And now we can easily do what we were asked to do, get dy dt in terms of dx dt. So now we can differentiate both sides with respect to t. So what we did was we first substituted, we got rid of z, because we had this little relationship here that allowed us to get rid of z. And now we're ready to differentiate both sides. So this is typical for a related rate problem. All right, so now let's differentiate this side with respect to t. Okay, so remember, x is the inner function and exponent 4 is the outer function. So first do the derivative of the outside, that will be 4x cubed. Now the derivative of the inside, that's the derivative of x, and with respect to time. All right, so there we have it. We should just multiply that 4 times 50 over there. So let's just do that. So we have dx dt is equal to 200 x cubed, sorry, dy dt is equal to 200 x cubed dx dt. So now we have a related rate. This is called our related rate equation, which relates the two rates, dx dt. It shows how dx dt and dy dt are related. All right. Okay, let's do another part to this problem, or a continuation. And let's say the problem continues as follows. It says, if we know what dx dt is, let's say dx dt is 2. And then we want to find dy dt when x is equal to 1. So we can do that. We have enough information using this equation. We're just going to substitute in. Okay, and let's do that. We'll just substitute in, and we have, using this equation here, we have dy dt is equal to 200. We want dy dt when x is equal to 1, so that would be 1 cubed, and we're told that dx dt is equal to 2. So we just put a 2 here. So dy dt is equal to 400 when x is equal to 1. Now we're going to do our first real related rate problem. Okay, related rate problems are, in general, there's some sort of word problem, and we have to set up an equation, and typically set up some equation and then differentiate both sides with respect to t. All right, so let's read this. It says the radius of a circle on your computer screensaver is increasing at the rate of 2 centimeters per second. All right, so what we're picturing over here is some sort of screensaver, and the screensaver like has this circle that's sort of growing. All right, it keeps getting bigger and bigger on your computer screen. All right, so imagine that happening on your screen, okay? Some circle that's spreading out, getting bigger. And it's growing, let's see, the radius, that is the radius of this circle, here's the radius, r. The radius is increasing at the rate of 2 centimeters per second. All right, so that's important. Increasing at this rate. What that tells us is that this information tells us that dr dt is equal to 2. All right, so we have that information. And now we want to know how fast is the area of the circle increasing when the radius is 5 centimeters. All right, so we want to know, so we have two variables here. Our variables are a for area and r for radius. And we want to know the relationship between the two. Okay, how are they related? Well, we know how the area is related to the radius of a circle, we have a formula for that. So typically, very often our equations in related rate problems come from some sort of geometric area or volume. All right, so in this case, we need the area of a circle, and we know that the area of a circle is pi r squared. So this is the relationship between our two variables, a and r. And now we want to know how fast is the area of the circle increasing. So what does that translate to? We want to know what is dA dt. That's how fast the area is changing. How fast is the area increasing? What is dA dt when the radius is 5? When r is equal to 5? Well, that's not hard to figure out because we have the relationship between a and r, and we're just going to do what we did before. We're going to differentiate both sides with respect to t. Okay, so let's do that. So here we have dA dt is equal to, and pi is not a variable, pi is a constant. Differentiate r squared by bringing the 2 down, subtracting 1 from the exponent, and then multiply by the derivative of the inside. That is the derivative of r with respect to t. So remember, we're differentiating both sides with respect to t. Okay, so what do we have here? Well, in this equation, we have this is what we call the related rate equation. This is the relationship between the two rates, the dA dt rate and the dr dt rate. So we just have to substitute in. We want to know what is dA dt when r is equal to 5, and we already know dr dt. dr dt is 2. So we have enough information here. We're going to put a 2 here for dr dt that we're given, and we're going to substitute a 5 for r. Okay, so let's do that now. So so first of all, dA dt is equal to, I'll put the 2 in front, 2 pi r times 2, because dr dt is always 2. So I did that substitution. And now when r is equal to 5, because we want to know when the radius is 5, what is dA dt? So when r is equal to 5, we'll substitute in r equal 5, and we have dA dt is equal to 2 pi times 5 times 2. 5 times 2 is 10, times 2 is 20, so that's 20 pi. And what are the units? Well, A is an area, and our units are the units that we're using are centimeters and seconds. So since A is an area, dA dt would be square centimeters per second. Okay, it's a rate, so it's per second. And an area, so it's not centimeters per second, but centimeters squared per second. Okay, because area is measured in square units. So that's dA dt when r is equal to 5. Okay, so now you're ready to do the last problem, problem 10, and let me give you that problem now. Okay, so here we go. Here's problem 10. I'm just going to move it over a little bit. You won't see the number, but I'm moving it over so you can see the entire problem. But it's right here. This is problem 10. All right, so this is very similar to the one we just did. Okay, so copy this, and you can do problem 10 now.